And share my screen. Okay, so before I continue, are there any questions from Wednesday's class or last week's class? We have discussed most all the models, the popular stochastic models, their characteristic functions, and we are now taking care of some of the loose ends before we move on to our numerical techniques. So if there are any questions, clarifications on chapter 1, you can ask now. Okay, so let me continue with our discussion on the change of measure. We were discussing our change of measure last class, and our initial context is always the risk neutral measure, and that we have seen last term also and did a quick recap last time. Well, the risk neutral measure is definitely the most common measure that we use in derivative pricing, but it is not the only one, because sometimes we are also faced with a stochastic interest rate. So when we are pricing derivatives with a stochastic interest rate, then what happens is there are two random variables. One is the stock price and other is the interest rate itself. So if I just try to do a risk neutral measure, then I will have two random variables inside my expectation, and it would be typically harder to evaluate. So when we have a stochastic interest rate, then the pricing calculation can be made more tractable when we can eliminate all other terms but this xt minus k plus. So just the value for the call option, let's say we are talking about an example call option, European call. So if I could eliminate all the other terms from inside the expectation, then it would be very easy for me. I just do a one dimension expectation. So we need a little bit of manipulation to get rid of the other random terms inside the expectation. So how do we do it? Basically, we are trying to eliminate the stochastic interest rate. So our structure is again this term structure. So P small t capital T, which is the time small t price, so current price of a zero coupon bond maturing at time capital T, with a face value of $1. So we always have 1 unit face value, and what is the current value of that 1 unit today? That's the question. Typically, we assume that our initial investments are of amount 1, and we use this term structure, this price PTT, as a numerator. So this is how we discount values in the future. So we define a new probability measure using this numerator. So what do? We say that C small t by PTT is expectation of the terminal ratio, the same ratio at the terminal time, C capital T by P capital T, but the expectation is taken under a new measure, P super capital T. So P super capital T is my new measure, which we will shortly define, and it is very simple. It is nothing but the discounting. We call this a capital T forward probability measure. And the change of measure calculation in this case would be relatively simple. So from the risk neutral measure Q to get to P capital T, what we will do is we will just note that expectation of this PTT by BT ratio under the risk neutral measure must be same as P0T B0. This is our typical risk neutrality consequence, that the ratio at terminal time, if I compute expectation of the terminal time ratio under my risk neutral measure, it will be same as today's value of that ratio. And now note that P capital T must be equal to 1. that is by definition, and I have taken B0 to be 1. So I know from this expression P0 capital T, which is a known quantity, so there is no uncertainty about it. So I can simply say that expectation under the risk neutral measure of 1 by B capital T P0T must be equal to 1. So I can insert the P0T term inside without any loss of generality and say that inverse of this product must have expectation 1 at time 0 under the risk neutral measure. And of course, I have to assume that this ratio is strictly positive. Otherwise, I will have problem. Okay. So this is our initial starting point. Any question? Okay. So therefore, what we do is we set our probability change derivative measure, because that's what we wanted to find. So our MT, which is our dPdQ, which changes the probabilities from Q probability to PT probability, risk neutral to our T forward probability, as just this ratio. This ratio is my MT, which would imply that under PT, expectation of this must be equal to 1, because expectation of MT is also defined like that. So we also note that expectation of PTTBT is this at any time point t. So this result that I wrote here for time 0, this one, this equation that I wrote for time 0, that must also be true for any other intermediate time point small t. So expectation under the Q measure at small time small t of this ratio must be equal to this. And again, I use the fact that PTT is 1 and P0T is known, etc. So we can write this as 1 by P0TBT, PTT, P0TBT. So I just divide both sides by P0T and eliminate PTT because it is equal to 1. So this is the expression that transfers values from time small t to any time capital T under the risk neutral measure. So this we will be using in our change of measure result. Okay, so this is the general structure so far, but I can make some additional assumptions to make it slightly simpler. So let's consider a single factor model. So we discussed the single factor model last term, where we said that the same source of uncertainty drives all the stock prices and bond prices in the market. So there is only one single source of uncertainty. That was a very simple model. And under that assumption, we derived a lot of nice results. And we also make the safe additional assumption of a constant or deterministic interest rate. So I take the interest rate as deterministic. So this is a special case of whatever we have discussed so far. At least in the short run, my interest rate is deterministic. Let C small t denote the time t price of the derivative that expires at time capital T. So C small t is the usual notation for the current price of the derivative. Now, following the previous discussion here, this change of probability measure discussion that we did here, what we can say is CT by BT. So CT expressed in terms of my numerator, the bond. So I am expressing everything as a ratio with respect to the bond. That must be equal to the expectation of the terminal ratio. So what do? I multiply this side by BT, and then I introduce my DQ DP inside, because my DQ DP has a simple structure, and I divide the whole thing by this expectation. I can do that because that I know is 1. So this I write out, my dq dp I write out, I simplify and take this P0T term outside. So what I will get is that BT P0T, this ratio of the two expectations must equal my CT. And of course, the expectation in the denominator is again 1. So simply I can say that CT is this expectation times P small t capital T, which is same as this. So is this okay? So I'm just making some changes in the numerator and denominator to change my numerator in order to change my probability measure. So I want to move from my Q probability to my PT probability. And there I am using this relationship. This is the relationship that drives the change of probability. Using that, I want to express the current price of the call, current price of the derivative in terms of the an expectation of the terminal derivative price only. So inside the expectation, I do not want any other thing to appear. The PTT will come outside. So is this clear so far? Or
Yes, sir.
Okay. And also note that if I did not make the assumption of a deterministic interest rate, then the result would be true up to 1.38 definitely. Because up to 1.38, I have not used the deterministic nature of the interest rate. Later on, I have taken things outside, but here I did not do anything like that. So taking these things two together, what we can do is we can now calculate the current value, time t value of the derivative, which is denoted by CT, either through this equation 138 or through this equation 139, where we use our cash account, the bond account as the numerator. So 138 is our usual method and is typically convenient. When we are pricing equity derivatives, we usually take interest rates and the cash account to be deterministic. As we discussed in the last term, that at least for ease of exposition, we will take the interest rates to be non-stochastic. That means I can do these simplifications of taking these factors outside, and the expectation will only be of C capital T. So the only expectation I need to calculate is that of C capital T. So when interest rates are stochastic, I cannot take this 1 by BT outside, of course. And therefore, I will need to find the joint distribution of B and C at the terminal time, BT and CT, because then I am here at equation 138. I have this ratio. I have to calculate the ratio, the expectation of the ratio. So I will need the joint distribution. So it will depend on what situation I am facing, that if I am using 139 to compute CT, then I will need a one-dimensional distribution, the T forward expectation of CT. And if I am using the direct risk neutral measure, then I am computing the expectation of a ratio. Of course, if interest rates are non-stochastic, then both reduce to the same thing and I have just one random variable to evaluate. But I need to also take care of the case where interest rate can be stochastic. And that is where working with 138 is not as simple as working with 139. Because in 139, through our change of measure, I have reduced number of random variables inside to just one. There is just one random variable inside. The other one has been handled through the change of measure. So again, I repeat that if I want to do the current time valuation with forward measures, if my interest rates are non-stochastic, it really won't matter much whether I use the risk neutral measure or I use the T forward measure. But if my interest rates are actually stochastic, then the T forward measure gives me a little bit of advantage. The advantage is in computation, I can avoid computing joint distributions and can only focus on a univariate distribution. And obviously, working with a univariate distribution is generally much easier than a bivariate distribution. So if we can find the t-forward distribution of C capital T, then it would be very good, convenient for our work. So whenever we are working with models that involve the term structure, for this Heston's model or the variance gamma model, everywhere we have been working with the term structure, the t-forward measure calculations are typically easier. So is that clear?
Yes, sir.
Okay. So we are more or less done with chapter 1. So we will just give a plan of work for the rest of the term. So what are we going to do in the other chapters? So that is what this last section talks about. So in the following chapters, we will talk about 3 major pricing methods. First, we'll talk about the transformation methods where we have the characteristic function. Then we will talk about numerical solution of PDEs and PIDs with difference equation approach. And finally, we will talk about Monte Carlo simulation. So why do we need all these things? We will of course talk about how each of them can be applied to different models and products. But the basic thing is that the more information we have, the faster computation methods we can use. So when we have the characteristic function of the log of the underlying asset, so if that is known to us, at least in implicit form or better in explicit form, then we can use the transform methods, because then it is direct Fourier application of Fourier transform and our computations will be fastest. If the next level of complexity is that if the process is Markov, but either I cannot find the characteristic function or the derivative price has path dependency. If I have path dependency, then I won't be typically having closed form expressions. Then using the Markov property, we can still use difference equation type numerical approaches and solve the PDs and PIDs for pricing. When all of these fail, the process is non-Markov or very high dimensional, the payoff is path dependent, or the derivative is extremely complicated so that we cannot write explicit PDs or PIDs, then we fall back on the Monte Carlo simulation methods. So Monte Carlo simulation methods happen to be the most general. It works every time, whatever the structure may be, but it is also the most expensive. So from now onward, what we are going to do is we are going to move from fastest, least expensive methods to more and more expensive methods. Why do we need to do that? Because if we have more information, we can use the least expensive methods. When we have less information, where information is less or the situation is more and more complicated, we have to move towards the more expensive methods. And finally, the last resort will be simulation. So that would be our plan of action for the rest of the course. Okay, so before I move on to chapter 2, I have put up this problem sets on the classroom. And from chapter 1, the first 5 problems I want you to start working on. So chapter 1 we have just finished, and there are 5 problems I have marked which you need to start working on. All right. So that is clear, then I can actually start talking about chapter 2. And chapter 2 is transform techniques. And recall that this is the place where I do know the characteristic function, and characteristic function of the distribution of asset prices is nothing but the Fourier transform of its PDF. So I do know the characteristic function, and hence we start this technique. So what is the set of admissible models? So the models I can handle here is all models for which a characteristic function for the asset price distribution exists. So I do know the characteristic function. What kind of contracts can I handle? I can handle all option types which are strictly path independent. So this is crucial. So we need European type path independent options, and the set of terminal payoffs also has to be restricted. It cannot be very complicated. If it becomes very complicated, then using transform techniques might be inadmissible. So we are paying something. So we are restricting on models. We are restricting on contract types so that we can use the best, fastest method, which is the Fourier transform method. What are the advantages? If I am able to use it, it allows for pricing under any model with a characteristic function that we have already said. It is very fast in the sense that I can price a set of n many options in order of n log n time. So on an average, for per option, I need only log n time. So a lot of computations will be common. So I can find a range of option prices in n log n time. So what it does is it generates n option prices in a single run. So there is no iterative method involved. In one single run, it will compute in n log n time n many option prices. Disadvantages, of course, there are a lot of restrictions. It is restricted to only path independent European options. I need a restricted set of terminal payoffs, each needing to be re-derived. So if I change my terminal payoffs, my computation has to be redone. It requires estimation of a parameter alpha. So I will introduce that very soon. So it requires estimation of a particular parameter alpha, which has to be chosen empirically for this method to run efficiently. It is like a damping factor. And we also know, numerically we know, that the transform methods are very inaccurate for highly out of the money options. So if the option is very out of the money, then my pricing method will become very inaccurate. So we can only do so much in a very restricted set, but when we can use it, it is very quick. So whenever possible, we will always try to use the transform methods. All right.
Sir, what is the out of the money options?
Out of the money option is an option for which if you currently go to the market, you will get a much lower price than the strike price. So if I have a call option, my strike price is 100 rupees, and suppose currently the stock is trading at 50 rupees.
Okay.
So it is very out of the money because I possibly have no chance of executing this option even in future.
Okay, sir.
Okay, so again, so let us start with the simple call option example. That's the best starting point. Path independent European option, call option is our first candidate. So we will see how we do call option pricing via the Fourier transform. And remember that when we are talking about the option pricing here with the transform method, we are not talking about one single option. We are basically talking about a range of options, and range in the sense of a range of strike prices. Because as I said, this transform method can actually do a range of option pricing in a single run. So that advantage we will highlight. So let X capital T be the T time price of the underlying security. So the stock X, FXT is the PDF under some equivalent martingale measure, and Q is Q of small xt is the density of the log of the underlying security. So small xt is nothing but log of capital XT. This is our usual notation. Again, small k is log of the strike price, capital K. CT small k is the price of a T maturity call with strike capital K equal to e to the power k. Because we will be writing everything in terms of small x, so we make this change of notation. We also use the log of the strike price. So wherever we had differences, we will use ratios. So phi nu be the characteristic function of small xt. So phi nu is nothing but this Fourier transform of qxt dx. Q is our density for the log. European call, the option price C capital T at small k, as I said, we are using small k, can be expressed like this. So suppose I have some normalizing constant capital C, which I will keep outside. This is nothing but the time discounting, interest rate calculation, etc. We will insert that later on, because again, for the time being, we will work with the assumption that interest rates are non-stochastic. So expectation at time small t of the call payoff xt minus k plus can be written as this integral k to infinity fx dx, which I will write in terms of the log transformation. So it will become e to the power x minus e to the power k under probability q. And finally, I use the notation C capital T small k to denote this original payoff. So this is my expression that I will be working with, k to infinity power x minus e to the power k qdx. Yes, any questions? Okay. So as I said, C depends on the equivalent martingale measure, discounting and other things. The Fourier transform of CTK, this expression, is defined as psi t nu. So psi t nu is e to the power I nu k CTK dk. Now I can insert the expression for CTK because CTK itself is an integral like this. So I have psi t nu equal to C integral minus infinity to infinity Q integral minus infinity to x e to the power I nu k e to the power x minus e to the power k dk dx, where I am using a change in the order of integration using the Fubini's theorem. Because it was supposed to be from k to infinity. So what I do is I make a change in the variable, change in the order. Now, if you try to evaluate this integral, you can check that this integral does not converge, because the inner integral, so this goes to infinity on both ends, so it will not converge. Is that okay? So when we try to evaluate this kind of integrals with unbounded range, in this case it will happen that it will not converge. Can you quickly check that?
Yes, sir. It will not converge.
So that's the first hurdle that we handle here, that in the original formulation, evaluating this integral runs into trouble. And that is where I mentioned earlier that I have to introduce a damping factor alpha. I have to introduce a damping factor alpha. Okay. Yeah. So what do? I reformulate the problem by defining a small c. So this is a new symbol. So this is capital C and this is small c. So I define small c as e to the power alpha k capital C. So what I do is I multiply the option premium by an exponential of the strike. So this k is log of strike, but alpha I have to choose. And this term becomes a damping component in the inner integral. So instead of capital C, if I now have small c here, and with this damping component, we can check that this integral will now converge. So again, if you quickly check, that would be good, that if I have an alpha, positive alpha, the integral will now converge. So now the redefined psi is e to the power I nu small c dk. So this is, it uses the same symbol. It is a bit of an abuse of notation, but the same psi I am using, but instead of capital C inside, I have now small c. So I have this additional term of e to the power alpha p. So as with the damping factor, the inner integral now converges, then using the above modified integral and some usual manipulations, what we can show is that this integral is equal to this expression. So I can explicitly evaluate this integral, which will appear inside. Okay. So the integral which will appear inside, that can be evaluated to be this expression here. So this is my integral evaluated. This is a relatively straightforward integration, so you can just check that. So thus, if we know the characteristic function of small x, this phi nu, and we can calculate psi t with the damping factor. So the Fourier transform of the modified call, it will look like this. So the whole expression now is e to the power I nu k c t k, small c now, and I know how to evaluate the inner integral. So finally, what I will have is this whole expression in equation 2.2. So is that okay? I'm just using the normal distribution result here. So I have transformed the inner integral, I have forced convergence, and then I know that this inner part can be actually shown to be equal to this. So I now insert it in psi t, and the final result using the normal characteristic function, normal distribution characteristic function, I say that will be equal to this expression. So is that fine? Just check this and tell me if this is okay.
So I think this is not coming from normal, but the phi b is defined as the characteristic function of the
Hmm.
log of
So,
sequence
so, so
difference.
it is just a change of variable inside.
Yes, yes,
Yeah.
yes.
So I don't need to write it out at this point. So all I need to recognize is the argument inside has been transformed in this particular way.
Yes, sir.
That is good enough. Because in any case, in any computation routine, I already have this kind of function stored inside. They will give me the values. Okay. So 2.2 is what I have with damping factor alpha, which appears inside and in the denominator. So of course you understand the choice of a proper alpha will be important. And then again the inverse Fourier transform to get back the original derivative price. So CTK I can recover using the inverse Fourier transform and remembering that capital C and small c is related through this e to the power alpha k. So I have to multiply this expression by e to the power minus alpha k. Because if I just do the inverse Fourier, I'll get small c. So I have to multiply by e to the power minus alpha. And you have to recognize that C capital T is a real number. This is a real number. So what we will do is we will treat this as an even function to get rid of the complex component, because the final result has to be a real number. So we'll do the integral from 0 to infinity and write that CTK is e to the power minus alpha k by pi, because there are two times here, 0 to infinity integral of this argument. Now, this is a little bit of a trick. And again, if you are not familiar with handling complex numbers, it might look unfamiliar. But what I am basically saying here is that you have the conjugacy in this integral. So the original integral is over the whole real line. So on the negative side, if I have a minus ib, on the positive side, I will have a plus ib. So that's how I try to merge them to get rid of the complex arguments. Is this clear to all of you? Because some of these results require a little bit of tricks or manipulations, and complex number appears all the time. We cannot help it because we are using the Fourier transform. So anyone wants to ask anything at this point about this? Okay. So to summarize, I am trying to price the call option using Fourier transforms, using characteristic function. I work with the log price process, but in the original form, the Fourier transform does not converge for my call price. So I use a damping factor alpha and redefine my Fourier transform of the call price. We show that with that damping factor, the integral actually converges. That was the purpose of the damping factor. And then, of course, we can evaluate the characteristic function for the call price, for the modified call price, like equation 2.2. And from that, we can recover the call price because it's a real number using this even function argument. And the final result is given by equation 2.6. So that's our approach for evaluating the price of an European call using the transform technique. There are some manipulations involved, some arguments involved, but the final result is an explicit, reasonably simple expression. So evaluation of that expression will be quite fast, reasonably fast. Okay. So the second part that we talk about here is about the put option. So same issue, pricing the put option using Fourier transform. We can work in a very similar manner. In fact, you can say that because it's a European option, why do I need to at all do the put option pricing? Because we have put call parity. We have already learned put call parity. So I know that we can only work with the call option. I can deduce the put option from the call option price. But as I mentioned earlier, that when we are doing option pricing here, we are not actually doing it for a single price. We are always looking at a range of possible true prices, because in the stock market, not only it is for numerical convenience, in the stock market, we always have a range of price between the bid price and the ask price. So if you look at the stock market quotation for any contract, you will see that actually there is no single price. There are two prices offered. One is the bid, one is the ask. So any price in between the bid and ask is a possible price. So that's why put call parity does not hold for the whole range naturally. So we do need a formulation for the put price separately. So similar notation. So again, I write PTK as the price, and I write strike as e to the power small k. So my expression here is for the put price. The notation is PTK, and the integral will look like this. So it's just e to the power k minus e to the power x. Otherwise, it will be the same. So these are the reverse of this thing. This was k to infinity, this one, and here it will be minus infinity to k e to the power k minus e to the power x, because it's just the converse of the call contract. So again, this integral, we know we will run into trouble when we are doing the integration. So we introduce again a damping factor, but this time for put option, we will need a negative alpha. We will need an alpha less than 0, and we define small p as e to the power alpha k capital P. Again, same discussion. We know phi nu, so I will write psi, the characteristic function of the put, in terms of phi, and using same type of tricks, we will have equation 2.9. So equation 2.9 relates the characteristic function of the put price with that of the log stock price, phi. And then using inverse Fourier transform, we can recover the put price from this psi expression using the typical integral. And again, put price is a real number, so I treat this as an even function. So my final expression is 2.13. The put price is given by e to the power minus alpha k by pi, integral 0 to infinity, e to the power I nu psi t. So obviously similar development, exactly mirror images, but we do need an explicit separate expression because we are faced with a range of prices in the real market. Okay. So is it clear so far?
Yes, sir.
Can you explain the reason why we are not using the put call parity?
So if you look up a stock market window now, okay, so we have done that last term, remember? We checked out the National Stock Exchange pages.
Yes.
Yeah, so we always had a range of prices. if you remember, we always had a bid price and an ask price, one for buying, one for selling. So it was actually a range which was always quoted in the market, and the transaction will happen somewhere inside that range. So in real life, when the contracts are alive, so before the expiry date, we do not have a unique price. We actually have a range of price. And obviously the put call parity cannot hold for a range of price. Remember, the put call parity was proved under this frictionless market. So there is no transaction cost and everything, which would mean that the bid and ask price would coincide. So then we have a unique price and put call parity will certainly hold. But in a real market where we do have transaction costs, etc., there is a positive, strictly positive gap between the bid and the ask price. And then we will need separate expressions.
So we cannot use this put call parity for evaluating price from the call option for the put option in the real markets.
Yes. So what happens is, to be absolutely precise, we have to calculate both of them. But sometimes what we do in the market is we take the mid-range price. The mid-range is bid plus ask by 2. So the midpoint of the bid and ask price, take that as the true price, and then we have put call parity at the mid-range price. But that is an approximation, because the next transaction may not happen at exactly the middle point. It may happen closer to the bid or closer to the ask price. When the option contracts are very highly traded, very liquid, as we say, then the gap between the bid and ask is very small, and this approximation will not harm. We can take the mid price as the true price, and calculations will be true for the whole range, practically the whole range. But when the contracts are not traded so frequently, and I have a bigger gap between the bid and ask, then I do need separate expressions. Okay.
Yes, sir.
All right. So maybe you should. All right. Share the screen. Okay. So I want to resume from here, this point where we would talk about evaluating the pricing integral using numerical integration. So how many of you remember numerical integration? We have all done it in our undergraduate days. Can you recall numerical integration?
Some of the rules, like
Some of the
trapezoidal, Simpsons, one
trapezoidal,
third.
Simpsons, yes, that will be enough. That will be enough. If you recall Simpson and trapezoidal, because we will talk about only those two. So that is fine. Okay, so now we have the characteristic function, and using the characteristic function, we have the call price and the put price. So how do we actually evaluate the inverse Fourier transform, an expression like 2.6? So when I have an expression like 2.6, an integral, I will obviously try to convert it into a sum, into a finite sum, and evaluate that sum. That's the numerical integration routine that we always do. So in this case, using 2.6, we will start by assuming that there is an upper bound for the integration. So of course, we cannot handle infinity. So we will take a large enough number, capital B, that will be our upper bound. So we will assume that the probability beyond that B is negligible, so we can simply ignore that part. That's what we always do. So we numerically integrate this truncated integral, because I have taken the upper bound as capital B, via the simple trapezoidal rule. Trapezoidal rule will work. So suppose n be the number of intervals, equidistant intervals. So n must be capital B by capital N, and that we call as our delta nu or eta, the distance between the integration points. So the evaluation points are eta apart. So jth point nu j is given by j minus 1 times eta. So from 0 up to capital B. So these are our endpoints. J equal to 1 to n plus 1, nu j are the evaluation points. We will discard the last term because the terms are exponentially decaying, so that it makes the summation suitable for a fast Fourier transform. And what we will do is we will approximate CTK. I write approximation because after all we are approximating it with a summation. So e to the power minus alpha k by pi is fine. Instead of the integral, now I have j equal to 1 to capital N, e to the power minus I nu j k. So I am evaluating this at nu j. Psi also evaluated at nu j, and wj is the step. So this is coming from the trapezoidal rule. So wj, the step weight, will be this expression, eta by 2 to 2 minus delta j minus 1. Or you can use Simpson's rule. So these are the two common numerical integration routines that we learned. So if I use trapezoidal rule, this will be the choice. If I use Simpson's rule, then I will get a similar result, a summation of this type with omega j now as 1/3 eta 3 plus minus 1 power j minus delta j minus capital N. And deltas are like, if j equal to 0, then delta is 1 and it is 0 otherwise. So deltas are like indicator functions. So here in wj or here in wj, the deltas will be 1 when I have the subscript equal to 0, and otherwise they vanish. So these are just corner point corrections. So deltas are for corner point corrections, end point connections, and the rest of the expression is coming from either trapezoidal rule or Simpson's rule. Simpson's 1/3 rule. That's how we learned it. So these are the possible numerical strategies. Now, even with that, we normally can quickly notice that this direct integration is not very efficient. It can be actually done faster. The direct Simpson's or trapezoidal rule integration that we outlined here is not really the most efficient thing that we can do. So Cooley and Tukey, the reference is 78, Cooley and Tukey developed an algorithm called the fast Fourier transform, FFT algorithm. And it provides a more efficient way of calculating this discrete inverse Fourier transforms with choosing the sample points as powers of 2. So the sample points are chosen in a particular way as powers of 2, and the weightage function that we showed earlier here in the Simpson or trapezoidal rule are now transformed into a more complicated formula like this. But the advantage is, it has been shown that this Cooley-Tukey FFT algorithm reduces the computational burden to n log n, where the original algorithm actually takes n square steps. So the original direct integration is n square steps, but the FFT is n log n, so which is much faster than the direct integration routines. So this algorithm is detailed in this reference, and they use an algorithm which is called a divide and conquer. The divide and conquer is like we do interval halving and take which one is closer to the solution, etc. But eventually, because of this 2 to the power screening, the computational burden is reduced to n log n. So are any of you familiar with numerical routines like this?
Yes, sir. In signal processing, we had done this.
Huh? Sorry?
In signal processing, we had done this,
In
but not
signal
everyone.
processing. Oh, acha, in signal processing. Right. Of course. Of course. these are of course used in signal processing. Okay, but if you are not familiar with this, just make yourself familiar with this fast Fourier transform and the 2 to the power n kind of logic, because this is a very powerful algorithm, and the explanation is not very complicated. The explanation is actually quite simple. So all I am doing is I am doing interval hubbing, successive hubbing. So that reduces the computational burden by a lot. And eventually, as I state here, and it can be checked, that you can reduce the computational burden a lot. Okay. So what we do is we convert our option pricing formula into this fast Fourier transform by creating a range of strikes around the particular strike for which we wish to calculate the accurate option price. Because we can always work with a range, as I said, so we will select a range so that the specific price where we really want to evaluate the option, that will be calculated very precisely. So it's like put it in the middle of the interval. So a typical case, let's talk about an example. A typical case would be an at the money option. So at the money option means right now the stock price is roughly equal to the strike price. So you are not yet at the expiry, but right now the stock price S small t is close to capital K. So in this case, we'll define the range of strikes in the log scale in the following way. So we'll take Km as one particular log strike as beta plus m minus 1 delta K, or beta plus m minus 1 lambda, with beta equal to log x naught. So log x naught is the day zero price minus lambda n by 2. So we are dividing the whole interval into delta K length pieces, and we are trying to make the midpoint. So this choice will cause the at the money strike to fall in the middle of our range of strikes. So we have a whole range of strikes from this beta up to log x naught plus lambda n. So if my strike price is close to log x naught at this point, then I will take a range which will be to the left and to the right of the current price, so that the current price falls in the middle. Is that clear? So this is just plus lambda n minus lambda n by 2 up to plus lambda n by 2 in n many steps. So our log x naught will fall in the middle. That's what this grid actually achieves, this grid here. So for any Km, the mth strike price, CTKM will be approximately equal to this integral psi t wj. Wj comes from here for each m equal to 1 to n. So I can write it out. I know how nu j is written, j minus 1 eta. I know how Km is written. It is m minus 1 delta K steps. I can take this beta, etc. things separately. So the final expression for the call price will be summation over minus lambda eta j minus 1 m minus 1. So remember that m comes from the grid of the strike and j comes from new j as in the original integration here, where we did new j equal to j minus 1 eta step sizes. So so we are basically looking at two-dimensional grid now, j minus 1 and m minus 1 with eta and delta steps, and this would be our final expression. Now, okay, so a little bit more of computational strategizing. So if we set lambda times eta, so lambda eta appears together as a product in this summation. So if I put lambda eta equal to 2 pi by capital N and xj, the xj choices here in the first Fourier transform, if the xj choices I take as e to the power minus I beta nu psi t nu j, wj, this expression inside, and beta as before log x naught minus lambda n by 2, then we get back the original first Fourier transform. So if I make these particular choices, lambda eta equal to 2 pi by n, and take this whole expression here as my choice of xj, then I will go back to the original Fourier transform as in here, 260. So using this expression, what will happen is that we can generate n many option prices, because I have a range of n many strikes, using n log n order multiplications. Because of this 2 to the power rule, my multiplication bar, the computation burden is now n log n. So what happens is, in this entire operation, I use n log n operations, but I get n many options. So my cost is like only order of log n per option. So even though if I were doing it for only one, then it's not an advantage, because direct integration for one single strike would be order of n. But because I'm doing it for n many, my cost per option is actually only of order log n. And that's where the first Fourier transform helps us. It is cheaper. The first Fourier transform is cheaper. So again, so is this clear? So I know that these expressions and things like that are typically not very exciting. They are boring, I understand. But when you are actually looking at algorithms which you need to run very fast, then this kind of manipulations are very, very important. In real-time stock market scenario, where quick computation, quick but reasonably precise computation is very important, there these things are valuable, extremely valuable. So is the logic clear?
Yes,
The
sir.
logic of first Fourier transform, is that clear? I know that the details are, the nitty-gritties are boring, but the logic has to be clearly understood.
Yes, sir.
So very soon we'll be getting into programming exercises, and for many of the Fourier transform routines, ready-made programs are already available. So we will see how it relates to our option pricing scenario, and actually how much time are we saving using these things. Okay, so I have this first Fourier transform with this 2 power routine, and we can make particular choices, and we see that our cost is like order of log n per option. I will just be off for a minute. Just give me a minute. Okay, sorry about that. So, so this first Fourier transform is where we are at. We are able to generate option prices. But this is an ideal scenario. So a word of caution that these n options are not likely to be exactly the n that we want. So because in a market, what we really want is option prices at some particular prices which are important for us. And if I use this grid, and this grid is a very simple linear grid, so equally spaced, that may not be exactly the grid that I really want. So for producing a sensible implied volatility surface, so implied volatility surface means we generate the option prices for different scenarios and then calculate the implied sigma square, the variance. And a plot of that variance with the different parameters is called an implied volatility surface. So we want to produce an implied volatility surface with points at market traded strikes. So at the strikes where options are now available in the market. But in the FFT method, our strikes are determined by this linear rule. So they are equispaced like this. And the market strikes may not be equispaced like that. They may have different gaps. Then this grid and the FFT grid, the actual realized grid in the market and the FFT grid will not match. We can, of course, modify the eta by modifying n, so take more or less number of steps, and which will also change all the strikes for which you get the option prices. So that will allow us to extract sufficient information to interpolate the volatility surface. So basically, we are trying to estimate a surface using a few of the grid points. So basically, we are evaluating it at some few points on a grid and then interpolate between successive points to get the surface. So we want that interpolation to be reasonably good, reasonably error-free. But if I try to do that by modifying, then my computational burden will of course increase. So it will become like order of n square if I want to evaluate n many strikes, because then I will no longer be able to efficiently use a divide and conquer type algorithm. So if I want flexibility so that I can estimate by my volatility surface precisely, I will have to give up on the efficiency a little bit to some extent. Okay. So with that, let me move on to the implementation. So actually how the algorithm will operate. So we have looked at this expression here for the call price, which actually has a two-dimensional grid in terms of k and in terms of mu. So I had two variables here, mu and k, which we have put in here together, mu j and km, so that at one go I compute the call price for multiple number of strikes. But how does it get computed in a program, in an algorithm? So the implementation part of FFT. So we have the characteristic function, which is phi for xt. We choose eta and we choose capital N equal to 2 to the power small. So this is our divide and conquer, the FFT, power of 2. So we'll go by like 16, 32, 64 like that. We choose lambda equal to 2 pi by n eta, so that lambda eta is 2 pi by n, as we have mentioned here. So I choose lambda eta equal to 2 pi by n. So once I have eta, I choose eta, then I automatically have lambda from n and 2 pi. Then nu j, steps nu j will be j minus 1 eta, and we have to set a particular value of alpha. This is a matter of choice, and typically alpha we find a good choice by looking at empirical performance of the algorithm, because the damping factor will be there, so we have to choose it smartly. Now let us form this vector x. This vector x is x1 to x capital N. How is it defined? X1 is eta by 2, this expression here that we have seen before from our characteristic function. Then this is the first term in the K grid. This is the first term, log x naught minus lambda n by 2 in the K, in the strike grid, times mu1, so that is mu1 will be 0. Then the phi evaluated at mu1. X2, similarly, everywhere in place of mu1, I put mu2, which is eta then, and so on till I get to capital N, which is the end of the grid. So from the start of the grid, I move up to the end of the grid and stack all these values. So I basically stack those values in a vector, where of course our C will depend on the martingale measure. For all practical purposes, with a constant interest rate, we will take C equal to e to the power minus RT. So if I have a constant interest rate, C will just be the discounting factor. So this vector is the input to the FFT routine. So this vector has all the relevant terms. All the relevant terms collected, that will be an input to the FFT routine. And the output again will be a vector of size n, which we call y equal to FFT of x, which will give me all the call prices at each of the strike prices. So the output y will be a vector of CT evaluated at all the admissible strike prices, K1, K2, Kn. Remember, these are log strike prices, which will be actually equal to this expression times real part of y1, real part of y2, etc. Because when we do this computation, we will get a complex number. So we have to take the real part. Remember that we used the same argument before, and we got rid of the complex part with the even function argument. So that's what we do here. We do the discounting and take the real part of this vector. So x is our input, y is the output called FFTX, which is the raw prices. But I know it's complex, so we take the real part and we discount it by this inverse Fourier function. So that is the algorithm for the first Fourier transform implementation. Okay. So then we are left with the question of alpha. So far, all we know is that the damping factor alpha must be positive for call prices and negative for put prices. But we don't have a theoretical clue about what the value should be like. So now if you refer to the book, there are some figures on pages 45 and 46. So let me open the book then. You can look at the pictures. So this is figure 2.1 for geometric Brownian motion for various values of alpha. we are looking at convergence. And the next figure is the tail of the integrand for various values. So this is the tail, and this is the whole integrand. And it is looking at how fast it is converging. So if we refer to those, then HITSA says that, so when we are using FFT methods, of course, results are sensitive to choice of alpha, n, and eta. We have seen that in these figures also. FFT methods will work in theory for any alpha. Well, there is no restriction, but we have to choose n and eta carefully. And HITSA shows that the most accurate results are achieved by using a large n and small eta, of course, but it becomes computationally expensive. And regarding alpha, his conclusions are that the optimal alpha should be in the range of 1 to 1.5. So an optimal range for alpha is between 1 and 1.5. Obviously, this is positive for call, negative for put. And obviously, larger n you have or smaller eta you have, the better results you will get, but more expensive the computation will become. And also, you need to guarantee that you are actually working out results for a useful range of strikes which are observed in the market, and that may not always happen. So those choices has to be made smartly. And alpha should be between 1 and 1.5. So the implementation, this is the basic algorithm, and the choice of alpha is empirically tested using this kind of graphs in HITSA, and these are the conclusions. Okay, so can we do better? So we know that we can do fast Fourier transform, but well, fast Fourier transform gives us results faster. We have only order of log n cost per option, but the spacing may not be to our advantage. We have this equal spacing, so we are basically constrained by this equal spacing, and the market observed strikes may not match with our equal spacing grid. So our estimated volatility surface and other estimates may not be as precise as we like. So can that be improved? So there is an alternative to fast Fourier transform, which is called fractional fast Fourier transform. What does it do? So as I said, fast Fourier transform dictates that lambda eta must be 2 pi by n and eta must be b by capital N. So we have only two free variables. So as soon as we choose n, eta is fixed and then lambda is fixed. So with only b and n, we are done. So with b and n, both eta, lambda, both are now fixed. So the whole spacing of our log strike price grid will be designed immediately as soon as we choose the upper bound and the n. Now, it would be good if we could eliminate the dependence between this number of terms n and the log strike spacing. The spacing and number of terms is now one-to-one connected. So we want to eliminate that dependence. This would allow us to use a smaller, if possible, a smaller n, smaller number of terms, but still get us an accurate set of option prices. How? Because we might be able to select more appropriate strike prices, market observed strike prices. We independently choose a lambda that is consistent with our market options. That will give us a better result with a smaller cost if we are able to space it as we want. And that's where the fractional FFT comes in. The fractional FFT computes a sum of this form. The sum is similar, same as before, 2 pi gamma j minus 1 m minus 1 x j. but it does so for any value of gamma, this parameter gamma inside. The standard FFT that we studied earlier is actually gamma equal to 1 by n, because I wanted that 2 pi by n relation. But if I break that relation, if I am free to choose any gamma, then what I have is called a fractional FFT. The summation can be computed without imposing the constraint, and that will mean that our grid spacing, we have a two-dimensional grid, right? One for the integral, the other for the log strike. These two grid spacing can be selected independent of one another. And that's the advantage we gain if we free up this parameter gamma. Earlier, we had it frozen. We had it frozen through this equation, lambda eta equal to 2 pi by n. So the spacings on two sides are essentially dictated one by the other. If we free it up, then we might be able to get the strike prices which we really want. Is this clear? Is this logic clear? So what I want to do is I want to break this connection between lambda and eta, the two step sizes, because then the two-dimensional grid is essentially dictated by one set of parameters. To break that, my strategy is to compute a sum of this type with a free parameter gamma, and then my grids can be selected independent of one another. So is this clear?
Yes, sir.
Okay, so then let us talk a little bit about the formation. So again, the references are here. In the fractional FFT, the fractional first Fourier transform, we define this sequence gm x gamma as summation j equal to 1 to n e to the power minus I 2 pi gamma j minus 1 n minus 1 x j. So this is coming from this type of term. This is the type of term that we are using here. This parameter gamma, in fact, may be any complex rational number. I can actually choose it as a complex number. It doesn't matter. The sum can be implemented via 3 2n point FFT steps. So I use 3 sets of FFT steps. We have already seen FFT steps before. These are the FFT steps, and we will need to use 3 of them. So what are these? So for an n-point fractional FFT on our vector xj, we define these sequences yj and zj in this form, where yj is given by this expression between 1 and n, and 0 after that. Zj is this expression, so it's like a tent. So from 1 to n, it is increasing with j, and then it goes down again because it is 2n minus j. And finally, x will be y plus iz. So I need 2 separate sequences because I want to generate the real part and the imaginary part. And then my complex number is x equal to y plus iz. And for the final implementation, I choose n equal to 2 to the power n. I choose eta and lambda independently. So this independently is the important term here. We calculate gamma equal to eta lambda by 2 pi. Eta and lambda I have chosen independently, but then I have to tie them up. Nu j as before. Alpha has to be selected. Now form this vector. Let us call this x. Summations of this form. Same logic, nu1, nu2, nu-n. Now y and z vectors are generated like this. Y, remember these are double length, 2n length sequences. Y will be like this. 0 from n+1 onwards, as we defined here. Zj will be the tent, so it goes up and then it comes down again, goes up to n-1, then again n-2, it comes back to 1. And with this y and z, I have as my input to the fractional FFT routine. The output will be y hat and z hat of the same size. I construct a vector xi by multiplying them element-wise. So I compute y hat, z hat from my FFT routine. The FFT routine was here. This is my FFT routine. I take the output, I multiply them element-wise and compute this vector xi. Again, 2n length, because there are 2n elements in each of them. Now xi is the input to the inverse FFT routine, and output will be xi hat. So inverse transformation of xi. Using this xi hat, the final call prices will be given by this discounting times the real part of xi1 and then successively discounted real parts of real part of successively discounted xis. So it is a complicated algorithm. So I start with a sequence of y and z like this. So I put them here to formulate the two y and z in the numerical routine. The outputs, I put them back together in xi, element-wise product, pass it through the inverse Fourier routine to get xi hat. From xi hat, I am finally able to calculate the call prices at the strikes where I want them to calculate. Remember, now I have broken the link between the eta and lambda grid. So I am able to calculate at a more convenient position. Real is the real part. Note that xi output had 2n elements, but in this computation, I am using only up to capital N. So the second half are not used. Considering lambda and eta are independent, we can choose lambda that would yield a range around log x naught with our desired gaps, desired moneyness. So suppose I want to go up to 25% above and 25% below, then all I need to do is choose a lambda equal to 2 into 0.25 by n. Also, typically n equal to 2 to the power small n, so this will be much smaller than a first Fourier technique. Because I no longer am bound by the connection, I can always take a smaller n. So like I can use 2 to the power 7 as opposed to 2 to the power 14, which is a huge difference. But the important part is I am no longer bound to have the same parameters in both the grids. I have broken the connection. So I can use smaller numbers here and choose my strike range very cleverly to get a more precise estimate. So on one axis, I choose the points I want. So my approximations will be better anyway. So what is the benefit? The benefit is on the other axis, I can take smaller number of points. Because I am close to the target point, my approximations need not be so precise. I will get a more efficient result then. So for my approximation grid, I take smaller number of points, but on my target strike grid, I get the exactly desired points. So my volatility surface estimation will take less of interpolation. Okay, before we close, I will just go back to this routine and talk a little bit about summing it up. So the first Fourier transform that we initially discussed were efficient, but I had this connection that both the grids the strike price grid and the numerical approximation grid were linked to each other. They are exactly connected to each other. And that gave me less freedom to choose points, because my market observed strikes may not match with the strikes that I can get here. That was the shortcut. We could still do it efficiently. So fast Fourier transform routine is quite popular, and you can choose alpha smartly to make it more efficient. But to break that connection, one can also use a fractional fast Fourier transform, which is an expansion on the FFT, where I break this link between lambda eta. And what I do is I create the sequences as per my convenience, the distances I choose as per my convenience, so that I am evaluating the summations at the appropriate strike prices. The benefit is I can use a smaller grid. I am not bound to choose the grid in the same way. So I can choose a smaller grid and save on computational time. Okay. So that's where I want to stop today. If there are any questions or clarifications, we can take them. All right. So we will stop today and let's meet next week.